Hello, everyone. Hello from my side. As Chairman mentioned, I am presenting this webinar live from Bruker XRM application lab located in Contiche, Belgium. This webinar is about 3D X-ray microscopy and its application in geosciences. And during this presentation, I will cover a few concepts regarding the X-ray microscopy, how it works, and then after that, I will give you a very short introduction on our devices and our micro-CT scanners. And after that, there will be some examples which I prepared regarding the applications in geosciences that we had so far. So starting with the micro-CT and what it is, well, X-ray microscopy, or also a micro-CT, as the name suggests, it has something to do with the X-rays. So it is an X-ray based imaging technique. And we know that X-rays can penetrate materials, and therefore we use this specific feature of the X-rays in order to image the internal structure of any kind of material without destroying them. There are three key components in the micro-CT scanning. The very first one is the X-ray source. The other one is the X-ray detector. And of course, the important one is the sample which goes in between the two. So most of us, we already know about the 2D images or 2D projections. If, we have a broken bone, or we have problems with our bone, or there is a problem with the tooth and we go to the dentist, then normally they send us in one room, and then there will be one image from the either tooth or the bones. Of course, this is only a 2D projection, or we call it also radiograph. So now imagine if we have this capsule, and then one 2D projection of that will look like this. What we do in the micro-CT or X-ray microscopy is that we take hundreds or thousands of these 2D projections while the sample is rotating. So actually many different 2D projections at different angles of the sample. So by having this many 2D projections, then by putting all of them next to each other and using specific algorithms, we can reconstruct a 3D representation of our sample. So that means that we put these 2D projections in a specific way together in order to map every point in a 3D dimension and then have a 3D representation of our sample. What we know about, well, actually the concept or the basic principle is in micro-CT is the same as what we have in the clinical CT. The only difference here is that in clinical CT, the patient or the sample is stationary, so it doesn't move. We cannot rotate the patient. And the detector and the source rotates around that one. But in micro-CT, it's different. The sample rotates, and the detector and X-ray source, they are stationary. So the resolution in medical CT is around 250 by to 500 micrometers. Well, this resolution could be enough for the human body, since we are relatively large, but if we need to image a mouse in a medical CT scanner, then this resolution might not be enough. So such image, when the resolution is not enough, we will have a kind of blurry image which does not give us many details. Now, in order to solve this problem, we increase the resolution, and then here is when micro-CTs are introduced. So the resolution for the micro-CTs can go even below micron, and you will see that if we compare the same scan of a mouse, then the details in a micro-CT with higher resolution will be much, much higher, and we can see a lot more features that it cannot be resolved by lower resolutions. A very important thing about the micro-CT is that the resolution in these systems, in the lab-based micro-CTs, are geometrical magnification. This is due to the cone beam shape that we have, and in order to increase the resolution or having higher resolutions, we need to put our sample closer to the X-ray source. Of course, when this goes close to the X-ray source, the field of view will be smaller. And now if you imagine that we have a capsule like that, and we want to have a high resolution, we go close to the source, and then therefore the field of view becomes smaller. And for larger samples, we need to go away from the source. This gives us a larger field of view, and then naturally the resolution will become a bit smaller. So the thing is that most of the time we are limited by the sample size in terms to achieve very high resolution scans. So if we want to have higher resolution scans, we need to prepare our samples or make them smaller and then run such scans on them. Well, the concept or the basic or what we do, we need in such imaging technique is that the partial absorption. This means that when we have X-rays going through the material, it gets absorbed. So if we don't have any absorption, then the image will be empty. We will not have anything. And if everything is being absorbed and then no X-rays can reach the detector, then therefore we will have only a black image. So what we do need is the partial absorption. For the partial, this partial absorption or this differential absorption between different material will give us a contrast. So here I put a slice of a rock sample in which that we do see different shades of gray. So by contrast, we mean that depending on the density of material that we have in the system, we will have different absorption coefficients being measured. And for each of them, a specific gray value will be assigned. And depending on the density of material, these shades of gray will be different. So for example, here, the brighter parts means that the density of material is higher, and the darker parts means the density or the absorption of X-rays are less at that point. Well, X-ray absorption is very much related to the atomic number, also X-ray energy, density, and atomic mass. So the very two important ones is the atomic number and X-ray energy. Actually, what we do measure is we measure the intensity of the X-rays that reach the detector after they travel through the sample. We already know the thickness of the sample. We already know the beam before the interaction with the sample. And what we measure is what we reach at the detector. So this is also another example of a rock sample. Here we do see different gray values, so some brighter parts, some darker parts, and also some very black parts. Normally, when we see these kind of like black parts, they are showing the pores, since pores are filled with air if the sample is not filled with liquids. And it has the lowest X-ray absorption, and it appears as black. So the brighter the material becomes, then the higher the density of that material will be. In the multi-material, when we have different materials or like different compositions in the system, the atomic number has the biggest influence on that one. But sometimes in some samples, we also have same material. So here is another example that in a specific sample, we have the same material. All of them are calcium carbonate, But the thing is that we still do see different values of or gray values in there. So the reason is because of the density variations. So some parts, if they have more porosity or they have more dense structure, then this affects the gray values that we do see in the images. Well, X-ray microscopy, let me run this one as well. The strength of this technique is that we can have a 3D view of internal object structure. So we can map the coordination of features in a 3 dimensions. We also can have selective visualizations of individual components or regions. I will talk about this one in the examples a bit more in detail, but the thing is that when we have a larger sample and we do want to have only a specific part of that, we can focus on that one and then have that part scanned. So we can have a selective visualization. So in this system, we not only do the qualitative measurements, but we also can run quantitative analysis. For example, we can run grain size distribution measurements or pore network, pore size distributions, and so on. As mentioned, in my opinion, the most powerful feature of this technique is its non-destructive nature. We don't need to destroy our samples in order to see the internal structure, and this can be very, very useful, for example, for irreplaceable samples like fossils or ancient artifacts that we do have, and we cannot really destroy them to see what is happening inside. And X-ray microscopy gives us the possibility to investigate such samples. And another very important thing about that is that we almost don't need to do any sample preparation, or at least if we need something, it is quite easy. So I would say this is an easy preparation sample technique that wouldn't be difficult, and it's also very easy to use. So in 3D microscopy, the workflow is as follows, that we start to position the sample inside the micro-CT. So the thing that we need to have in mind is that we just have to fix the sample inside in a way that it does not move during the scan. Then the scan runs. 2D projection images at different rotation angles will be acquired or will be recorded. After that, we put these two 2D projections into each other. We call it, we reconstruct the data set, and then it gives us a 3D, well, actually 3D representation or a 3D volume of the sample that we have scanned. And then based on the contrast and also the materials that we would like to do the measurements on them, we can analyze these 3D volumes. So after this small introduction to XRM technique, I will just give you a short introduction about Bruker, who we are, and after that we will have a quick overview on the devices and our micro-CTs. Well, the company profile, this is how Bruker looks like in Belgium. This is the X-ray microscopy or micro-CT manufacturing base in Contick, Belgium. So SkyScan, or these micro-CT scanners, it started in 1996, and in 2012 it became part of the Bruker group. So headquarters, as I mentioned, it is based in Contick, Belgium, and these micro-CTs can be used in life science and material science. We have more than 1,600 installations worldwide. And not only the hardware or the micro-CTs, the devices itself, we also provide software in order to do the analysis, to do the reconstruction. I will explain about this one a bit later. So about the micro-CTs that we normally use in the material science, there are 3 benchtops. 1275, 1272, 1273, and one floor standing high resolution, well, actually nano resolution scanner, which is 2214. In a more detail, we will discuss these devices, each of them, the strength of them. So SkyScan 1275 is actually a very easy to use scanner and also very, very suitable for the fast scans. It has a very high ability to to run automated procedures in there. So all the benchtop scanners, they actually don't need any kind of practically no maintenance is required since they have sealed source in them, and they don't need compressed air or any kind of liquid for the cooling purposes. So the only thing is that we take them, we put them on a fixed and sturdy bench or desk and connect it to the domestic plug, and that's it. The scanner is ready to use. So for 1275, it is also it has the possibility to set up, we call it push button scans. So this means that everything is automated in the background. We set all the parameters, and then the only thing that we need is to like really literally push this button, and the rest will be done automatically. The key technology about this system is that it can produce up to X-rays up to 100 kilovolt of energy with a 3 megapixel flat panel. We have a 3-position filter changer for that one, and the pixel size can go to around 4 microns for small samples, of course. This device can be equipped with a sample changer, which has 16 different positions. So for those who would like to have a faster scanning procedure day and night and without any problems, then this sample changer can be installed very easily on the device, and then by using that push button automated procedure, then all the samples will be scanned automatically, and at the end the data will be out for us. So the procedure would be something like this. We set up everything in the background, and then pushing the green button, then scan starts, reconstruction will be done, and the results will be displayed in cross sections in our visualization software. So it could be CTWalks or Data Viewer. We'll talk about these software package a bit later as well. So in the benchtop side, if we would like to go into larger samples and also higher density samples and need more energy, then we can move to 1273, which is the same as 1275. It is just ready to use, being connected to the domestic power plug, and that's it. Even though it is a benchtop, but still it can accommodate samples as large as 0.5 meter height and 300 millimeters diameter. This system can produce X-rays with an energy of up to 130 kilovolts, and it has a large 6 megapixels flat panel. The filter changer, it has 8 different positions, and everything can be done by a click from the software. So actually for changing the filters, there is no need to open the scanner or stop anything. It can be done from the software. And the pixel size can go down to 3 microns, again, for the small samples. And so, yes. Well, in the benchtop, we saw that if we want a fast, being able to be automated, we go for 1275. If we need more power and larger chambers, sample chamber, we go to 1273. But if we go to the side, the higher resolution side, we do have the 1272 device, in which the pixel size can go down to 450 nanometers for high resolution scans. This device can produce X-rays up to 100 kV energy, and it is equipped with a 16 megapixel CMOS detector. The filter changer is also automatic. It has 6 positions, and everything can be done by one click from the software. So no physical interaction with the device is required in that sense. This device can also equip with a sample changer, again, 16 different positions, and this is for, again, for increase the throughput of the scanner. And when we need everything all together, we want high resolution scans, we want large chamber size, we want high energies, then we have our floor standing system 2214, which can provide us real special resolutions down to 500 nanometers, so a sub-micron. This device can be equipped with 4 different cameras or detectors. 3 of them are CMOS and 1 extra large flat panel with 6 megapixels. So the thing is that not all of these cameras need to be purchased at the beginning or anything. So depending of the request or the requirement, one can go for only 1 or 2 cameras. But the important thing is that all the mechanics and everything is already inside the system. So if in the future someone needs other cameras and would like to equip his or her device with more cameras, it will be just a plug and play. So mechanics are there. There will be no downtime. There will be no very major changes in the system. Everything will be ready over there. The X-ray tube in this system can produce X-rays with an energy up to 160 kilovolts for, as we mentioned, 4 different detectors. We have 6 position automatic filter changer for selecting the optimum energy during the scans. And the pixel size with the CMOS camera can go down to 60 nanometers. There are some other plugins that might be of interest for some people, especially the material testing stage, that we can run compression and tensile testing on the material. So for example, compression on the rock samples is quite popular. These stages are made in a way that they don't need any plugs or anything. They will just be plugged on the stage inside the scanner. And then since there are no plugs, no cables in there, there will be no restrictions regarding the rotation of these stages during the scans. They are also made of materials transparent to X-ray, and therefore they will not interfere with our scans. There are also cooling stages and heating stages available for those who might have interest. And there are different sample holders that can be provided, like tubes, foams, and special shape holders in there. So at the beginning, I mentioned that with all of our devices, a comprehensive software 3D suite will be provided as well. And this comprehensive software, it includes everything that one need after the scan up to the very last stage, which is the sophisticated and advanced analysis. So when we do the scans, when we acquire the 2D projections, the very first step that we need to do is to put them together and then reconstruct the data set. So our reconstruction software is GPU accelerated, and it reduces the reconstruction time significantly. After reconstruction, we have 3D inspection data viewer software. So this is for fast inspection. We go through the sample and we want to see if there are any specific features of interest at the beginning. We also can do the distance measurements in this software and so on. For 3D visualization, we do offer two different software, CT-Vol and CT-Vox, in which we can do surface and volume rendering and adjustment of coloring and transparency. This will be shown in a couple of examples that I have provided for you. We can prepare animated movies for conferences, teaching purposes, presentations, and so on. And we can also export surface rendered models in STL format for example, for 3D printers or to compare with CAD drawings and so on. And last but not least, CTAN is used for the CT image analysis and image processing. There are many parameters that we can do or we can measure by using this software, for example, morphometric analysis and densitometry, so on. I will show you a few examples of what kind of measurements we can do in there. So here we go for the application overview. We mentioned it already. X-ray microscopy, micro-CT, it enables us to do non-destructive characterization of a wide variety of geomaterials. We are really not that much limited by the size, so we can have these scans on different sample sizes. And as I mentioned, we can have also quantitative analysis on structural parameters, such as grain size distribution, pore size distribution, not only pore size, but we can also go for the open and closed porosity and the connectivity between them and so on. Depending on the contrast, of course, we can run and do the calculate of the distribution of the mineral phases in 3D as well. And we can correlate the sample structure with mechanical properties by in situ mechanical testing. So I will show you this one, an example from that one as well. And well, not only the static properties, but we also can capture some dynamic features as well. For example, to visualize fluid flow, crystallization, dissolution, and so those processes that can be captured in a micro-CT timing frame. The very first example that I have for you here is a gold ore. So on the right-hand side, what we can see is a 9-micron voxel size scan, which is done by 1275 in 29 minutes. Here we have a 3D rendered volume of this sample. And depending on the contrast, since the gold mineral has higher density compared to the surrounding, then we can isolate these specific features and extract them from the bulk volume and then run the measurements on that one. So for example, here we have a measurement on the size of these particles in the sample, and it is color-coded for a better visualization. Red represents larger ones, and so it goes towards blue, it becomes smaller. Another example that we have here is about copper ore. So the sample itself is about 5 centimeter large. So this is the size of the sample. And we have done a 25 microns voxel size on this as well. So the red box over here, it shows the area which is scanned. And here we have a 3D rendered volume. So I just put a 3D rendered volume. Of course, we can see the internal structure as well and see different slices in 3D as well. So what we have here is on top, we have a 3D animation of particle size distribution that we do have here from a sample. We see that since the contrast of these particles are higher than the surrounding, we can isolate them and then we can show them in a nice way. So it can be again extracted from the bulk volume and being analyzed in terms of the size or in terms of the shape and so many different parameters. Here what we have is that we have a region of interest inside a sample. The darker parts, they show the pores, and the brighter ones, they show the the grains, and we can run the analysis or the distribution of the size on both of these two features, not only pores, but also the grains as well. And on the right-hand side, we do have a pore size distribution being shown in 3D. So here, this is a 3D rendered volume of the sample. You see it how it looks like. This is actually the digital twin of the sample, and the upper part is the extracted pore network and the measured one. So in terms of the size of the pores. Well, I mentioned that this technique could be very, very useful when we don't want, well, we have samples that we cannot destroy them. For example, here we have an insect inside the amber. So it can be nicely scanned and then see the structure of the insect inside that one with a voxel size of 7 microns and a scan time of 20 minutes without touching the sample and without destroying it. Another very nice use of that is in diamond industry, especially when we have the raw diamond and we have some inclusions in that one, for example, over here. And we would like to do the measurement and see that what would be the best out of this raw diamond, so without having these inclusions inside. Such inclusions, they might reduce the value of the end product, and then therefore MicroCT gives us the possibility and opportunity to see these defects and do the designs inside such volumes in a way to avoid them and also get the most out of them well, for having the best end value from the products. So for higher resolutions, here we have samples from 1272. This is a 2 micron microplug, and the resolution is about 1 micron. So the voxel size represents 1 micron of data. And we do have 3D rendered volume of the samples in here. So these are 2 different volumes being overlapped on each other. This part is the 3D rendered of the total sample, and here is the extracted pore from that one. So for the visualization purposes, we can put these next to each other and have nicer pictures and also better visualizations on that one. In here, the pore network is extracted and also being analyzed in terms of their thickness. So we can do the measurement and then show them in a way that, okay, where the larger ones are located and where are the smaller ones. And this shows us the visualization in 3D. Another sample that I have prepared for you is this 2 millimeter microplug with, again, 1 micron resolution scan. So in data viewer or in inspection software, what we do see is that these 2D slices in 3 different directions. We have the XY direction, which is the horizontal slice through the sample, and we do have the XZ and ZY slices, which are the vertical in the Z direction as well. Well, we mentioned we do have the 3D visualization of the sample and also extracted pores from such samples. The 2 examples that I'm showing here is one of them is a rock sample with fossils. It's the voxel size is about 2 microns, and here again we do see that it is color coded based on the thickness of the material inside the system. And in this one, well, actually there are some cracks or the planes inside the sample. These planes again can be extracted and also analyzed in terms of the thickness and the thickness variations through these cracks or these specific sheets that we have inside the sample. This is an example from a Castlegate sandstone sample done by 2214. Thank you to Shell, which is one of our customers. So here we do have the 3D visualization or 3D rendered volume of this sample. Also, we do see that we have different mineral phases, since it shows us different different intensities of gray values over here. And if we zoom a bit more on one specific part of that one and then have a look on this over here, what we can also see is the intergranular pores, since it can be quite important for further analysis or measurements, and also further running some simulations on the samples, for example, for digital rock physics purposes and so on. And the plug itself was 5.5 millimeters of diameter, and here we could reach a 2.1 micron pixel size. Another example that we have here, we can push the resolution to the higher ones. So here we have a 4 millimeter chalk sample. In here, again, the pores are being extracted and color-coded based on their sizes. The resolution of this one is 800 nanometers, and with a total scan time of 3 hours. So many details can be seen in the 2D slices as well. Darker parts, they represent the pores. We have different shapes. We have different sizes of them. All of these, they can be quantitatively measured. And also we have different gray values, which shows us that we have different materials being in such samples. So sometimes for the heterogeneity investigation purposes, we can go to the larger samples. For example, here we have a 1.5-inch rock core. And when we do the scans of these ones at like 5 micron resolution, we do see that there is kind of like a layering in this sample. And in the middle part, we have a higher porosity layer, so to say, with relatively small pore sizes. And then over here we have pores with different shapes and also some inclusions in there and so on. So this can be scanned at such resolutions, even larger scans, in order to see the heterogeneity and the changing of the layers inside the samples. Here we go a bit towards the concrete. This is a scan of the concrete core, a horizontal slice of that one and a vertical slice through that one. Again, we do see different material inside it, and also some pores with different sizes. This is a 2-inch concrete core with 28 micron voxel size of the full sample being inside the field of view. This scan, for example, takes about 4 hours. And what we also can do, not only the global analysis of the features of interest, but we can also run individual object analysis. So, for example, here in this example, we extracted the single pores one by one, and then we measured them individually and separately. And here, for example, we can show that, okay, how many objects we would have in this part of the sample. It's around 8,000 objects. And this shows us the variation of the sizes of each individual object of being presented in such samples. Another example from concrete is the steel fibers in concrete. These features, they can be also extracted. As you can see over here, it is a 3D representation of that one. And we can run the analysis on these fibers in terms of, for example, the direction of the fibers, how they are located inside the sample, and also thickness analysis. Here, the color codes, or the different colors, they are showing the direction of the fibers. So the more horizontal they become, the redder they get, and then the vertical ones, they are shown in more blue. So this is, again, only for the visualization purposes. For each fiber, we also have a CSV file being exported from the measurement device, measurement software, and it gives us the exact values regarding each of them. Going a bit away from the static features, here we have a bit more dynamic. So this is an example of using the material testing stage at which the core was located inside this testing stage, and then the compression was applied to that one. What we could see at different stages by scanning is that how the sample failure occurs. At the same time, we can also measure the force which is applied to the system and then see exactly what happens to that one. Another example for more dynamic sample is a salt crust formation on a Bentheimer sandstone. So for example, here we do see that how salt being deposited on the outer surface of this sandstone, and we can scan it at different time steps. And at each time step, for example, here we do see that at the very beginning, the parts which are deposited are shown in white, and then they become bluer as we go or proceed through the time. So this can be also a nice feature in order to be captured during the scans, again, at 5 micron voxel size with 30 minutes scans. Well, this was the last example, and this brings me to the conclusion. Only a small summary about what we discussed so far is that the XRM benefits, as we mentioned, we can have the 3D view of the internal object structure without destroying them. So a non-destructive technique that gives us a lot of information, not only about the surface of the samples, but also about the internal structures of that one. We can run this technique, or we can use this technique on a variety of the materials and samples in terms of both their nature and also their sizes. And we could have selective visualizations of individual components. We would like to focus on a specific feature, for example, pores, grains, fibers, and so on. We could do both qualitative and quantitative analysis on features of interest. And as we mentioned, the sample preparation is almost either none, or it's very, very easy to implement. I would like to thank you, everyone, for your time. I hope this presentation could be useful of you. If there are any questions, then I will be happy to answer.